Welcome to Chapter 12, Science. Today we're going to jump into this enormous topic, go through some of its strengths, some of its weaknesses, and really look at science from a critical thinking perspective. I know that many of you are in a scientifically based program, and today we're going to question some of the assumptions. What is the scientist thinking as she evaluates this glass flask? Who knows, right? She's probably thinking, hopefully, I look like a scientist because this is a stage photo for a textbook. But we know that in the real scientific world, all of the observations she is making are very controlled and linear and rational and follow a checklist, right? This is a very cerebral part of your brain that engages in science. Science is not really worried about how you feel, it is more about how you think. If you can't measure it, it doesn't exist. So, this is the scientific mindset. This is the way of thinking that is much different than using our emotional brain in that side of our, humanity. So, what is science? Science rests upon reasoning that moves from an observation, measurable facts, to testable explanations for these facts. So, you observe something and you say, listen, the apple's fallen out of the tree. I think there's something called gravity. I'm going to measure this and see if it happens over and over and over again. And then you have an explanation that you can test. And no matter how many times you test it, the same result seems to come back. Scientists discover, observe, collect facts in a systematic manner to explain data and relationships, right? It is all very systematic, it is controlled, is repeatable, and this is what makes it science. We can rely on it. It is a foundation that we can build upon. It is something that makes us feel safe and secure. It must be true because science said so. Modern science has a profound impact on our lives. Absolutely. And it has become so pervasive that we tend to perceive it as a natural method for obtaining and testing knowledge about the world. We have grown up with science. Science has been around our entire lives. Having said that, there's a large part of human history where science wasn't around. Science did not exist. So, we must examine the development of modern science as well as what are the assumptions underlying science. Science should also be questioned. If you learn one thing in this course, it is you need to question the way you're thinking. And I feel like sometimes as soon as we say, okay, listen, it is scientifically proven, we shut down our critical thinking minds and we kind of accept what is being presented to us. Okay, Copernicus was an early scientist. He was a mathematician, astronomist, and he observed for the first time that the earth revolves around the sun and not the other way around. And he took a lot of flack because of it. People didn't believe him. But he used science, he used evidence based reasoning to convince people, and eventually, after a long time, they accepted this theory. Because before, the theory was that the earth was the center of the universe and everything revolved around it. The kind of the way that I don't know, a 4-year-old operates in the world. Like, I'm in the middle of the world and everything is going to operate and rotate around me and my desires. We felt like that's the way that earth must be. God placed earth in the middle of the universe and everything rotated around it until Copernicus came along and he used that fancy measuring tool he has in his hand and some other complicated math to demonstrate that, in fact, it was the other way around. Assumptions underlying science. So science is the primary way in which Western culture, right, the culture that most of us grew up in, perceives and interprets reality. However, it is important to keep in mind that science is a system. It is created by humans, and as such, it is based on a particular set of assumptions, right? And these assumptions include something that is called imperialistic, objective materialism, predictability, and unity. These are foundational ideas of science, and it is largely Western, right? We travel outside of the Western world and we realize there's cultures out there that base big decisions on religion or I don't know, tradition or their culture. They're not all rooted in science. And we're so quick here in the West to dismiss any idea or explanation that is not rooted in empirical evidence that is objective, material, predictable, and in unity. Okay, so imperialistic means simply physical senses, right? You have to see it, you have to taste it, you have to hear it, right? Unless you can do those things, it does not exist. Objectivity, we can observe it in the study of the physical world without bias. So you have to step back, you have to remove all your bias and be able to observe something objectively. The next one is materialism. So everything in the universe is made up of physical matter, right? We aren't talking about ghosts or spirits or something that you can't physically put your hands on. Predictability, the universe is composed of interconnected causal relationships, right? And unity. The universe has an underlying unified dynamic structure. These are the foundational ideas of science. This is the bedrock that makes up the entire way of thinking. Is science the best tool for learning about the world? This is such an interesting question, and a lot of it will probably be cultural. It will be based on where you grew up, the culture that influenced you the most. And if you grew up in a Western culture, the answer to this question is probably yes. People would argue that science is the only way to really understand or know something. And without science, you can't be sure. You really just don't know. Okay, but what are the limitations of science? So science does have some limitations. So the first one is it's based on sensory experience, right? That is the foundation of science. Is if we can sense it, we can measure it. And the basis of science is the existence of the physical world. So this is the question. Are there things that human beings can't see and hear and taste and feel and touch? Absolutely they are. You know, you've seen these experiments where they have like a sound and they're playing it out loud. And certain generations as they get older can no longer hear that sound because they can't detect it. Or the idea of a dog whistle, right? That you can blow a dog whistle and the dog can hear it and you can't. Or the idea of smell, right? Look at dogs again. They can their sense of smell is 100 times better than human beings. Or look at, you know, eagles. Their ability to see is so much better. So part of the limitation is that we believe that everything is empirical. It has to be sensed by our senses. But I would argue there are things that we cannot see, right? There are things that we cannot touch. And that maybe not everything can be boiled down to logic, right? And maybe you can't always connect two events. Things happen all the time, and they call these mysteries or miracles or divine intervention. These are things that are beyond our comprehension, right? It also, like, think about this. Are there times throughout human history where human beings could not explain things through science? Absolutely. There are still things that we struggle with, big problems and issues that we struggle with that we can't explain. So part of the limitation is that we are limited in what we can measure and what we can see. So I do feel like that is one of the big downfalls of science. Belief that there are channels on Mars. Okay, so this is the other thing that's interesting is our brain tends to impose order where there isn't any. So when things are random, they tend to look at them and construct a story. Our mind wants to have an explanation. Our mind does not like unknown things. So this is an example of when scientists thought there were channels on Mars because they just couldn't see it that well until we had a satellite that went there, took pictures, and we understand that that is really not reality. But it was our brain trying to put, two and two together, things that may be related, but there's no, causation. So correlation without causation. Religious belief that humans are special creations. So the religious belief that humans are qualitatively different from other animals is one of the underlying assumptions of modern science. And so this is really interesting that there are some strong religious beliefs that we are different, that we are not risen apes, that we are fallen angels, that we have a direct connection to God. And that is, it is an interesting and sometimes dangerous thought, because if that is the case, then a lot of people believe that everything else on this planet is here to serve us, is here to make our life easier, is here to ensure our survival, to ensure our well-being. And based on modern science and what's happening in the world, that has not gone over so well, right? It's not gone over so well for the planet or the animals or our air or our water or our ecosystem, right? That idea that we are somehow different and maybe above the rest of our planet is something that has caused issues and will continue to. So the scientific method is dynamic with analysis returning to the observation. Yeah, it is a loop, right? You know this because we learned this in probably grade 6 science, that you go from experimentation and testing to creating a hypothesis or interpretation to observation and then back up. It's this continual kind of circle of, as we learn more, we begin to ask more questions, and those questions are based on experiments and testing, and we create hypotheses and we have observations, and it goes on and on and on, right? This is part of the exciting thing about science, is the reason we know so much today isn't because when we were born we kind of showed up in the world and learned and discovered everything ourselves, is because we've been able to stand on the shoulders of those people before us and build on their knowledge, which is really, this is why it's an exciting time to be alive. We have never known so much about the world as we know today. But in 100 years, they're going to look back at us and think, oh my gosh, those people living back in the 2000s were so ignorant. They knew nothing. They knew nothing. The scientific method is a process of involving rigorous, systematic applications of observation and experimentation. It involves these steps. You have to start with a problem. You have to develop an initial hypothesis, gather additional information, and refine your hypothesis. You need to test it and then evaluate the hypothesis based on the results of the testing or the experiment. Again, you have seen this since grade 6, right? We've been studying the scientific method for a long time. I'm sure in high school, in bio and chem, and even grade 9 and 10, you went through this, and again here at the college level. Darwin went to the Galapagos, right outside of Peru, and he spent a lot of time studying animals. And this is where Darwin's famous theory of evolution, survival of the fittest, came from. And he spent years and years meticulously drawing different animals. So this really helped with the scientific community in looking at evolution and looking at species how they're related, and which species survived and which ones died off. So Darwin is obviously one of the most famous scientists in history for dedicating so many years of his life to traveling around and really painstakingly recording all these details. Margaret Mead. Okay, so Margaret Mead is known because she spent time studying cultures that were more laid back than Western culture. There's lots, right? Some people say that Western culture, we work too much, we're too uptight. But she was criticized later about the way that she gathered information. And a lot of it was anecdotal, meaning that it wasn't necessarily based on science, it was based on what she observed. And the challenge with that is, as we know, our eyes interpret situations. They aren't like a recorder. They don't just record it and then we use that. It manipulates it. And we've talked about this in previous classes, that everything we observe passes through a filter. And that filter is based on our culture, it's based on our education, our race, our age. All of those things change the picture. And so after years of research, Margaret Mead's methods were tested and they were questioned, because a lot of it was based on what she saw and her interpretation of those events, not necessarily precisely what she was observing. And her theory was that women who grew up in these cultures that were a bit more laid back were happier. Maybe it was right, but it was just the method. Minnesota twin study. This is an interesting one. So this is a really long study they started back in 1989, where they took identical twins and they followed their life to try to figure out that whole argument of genetics versus environment. Like what determines your outcome in life? Is it programmed in you? Is it in your DNA? And that is a story that unfolds regardless of what you end up doing. Or is it the environment that shapes who you are and what you become and what you believe? And one of the interesting findings is they said that 40% of your likelihood of being religious or praying or going to church was 40% genetic. So they're really trying to extrapolate, okay, what is genetic versus what is environmental? And I thought that was interesting. It's in your textbook. There's a couple more details in there, but that was one that kind of jumped out in my mind. So evaluating a scientific hypothesis. When evaluating a hypothesis, you need to make sure the following criteria are appropriate. Is it relevant to the problem under investigation? Is it consistent with well-established theories? Is it the simplest explanation for the problem? And does it provide a testable and falsible explanation of the problem? And can it be used to predict the outcome in similar events, right? It's really important that if you discover something, that you can repeat it over and over and again, and it becomes predictable. Like the gravity example I gave, it is something that's very predictable. It happens 100% of the time. If you throw something up in the air, it falls to the ground, right? Unless obviously you've changed the variables, helium, I don't know, all the other things you can do to have something not hit the ground after you throw it up in the air. But you hopefully understand what I'm saying. All swans are white, okay, was falsible. And what that means is, scientists hate this, but they hate it. But you just have to discover one exception to the rule, and then your whole hypothesis is thrown out the window. So for a long time, they thought that all swans were white, until someone traveled to, anyone want to guess? Australia, and found a black swan. And then overnight, just like that, the hypothesis that all swans are white was shattered. Now they come in different colors. I think I knew that. Hopefully you knew that. I don't know. Albert Einstein raised the question whether scientists should refuse to engage in potentially destructive research. So Albert Einstein, he grew up in Europe. He was Jewish, and so he had to flee Europe when the Nazis took over, and he went to the States to study there. And World War II was taking place, and they dropped the atomic bomb on Hiroshima. And this is when he became very vocal about engaging in science that can be destructive. So he thought, listen, the scientific method should not be used to hurt people, to cause death and misery and destruction. It should be used for good. And he's right? There's a lot of potential for science to be used for evil. And it has been, right? I mean, there's some examples in the world right now of science being used in ways that probably don't align with our values and ideals as human beings. Okay, pseudoscience is a body of explanations or hypothesis that is an attempt to gain legitimacy, right? But it masquerades as science. So unlike science, which uses a systematic observation, reasoning, testing, pseudoscience is based on emotional appeals, superstition, and rhetoric. Astronomy is an example of pseudoscience. So you've seen those, I think, right? Like when you're born on a certain date, you have a sign, and based on that sign, you'll get advice. And they do this. They used to do it in the newspapers and magazines. I'm sure there's websites now where you can go every day and it'll say, okay, according to your sign, this is what's going to happen to you this week. Kind of like fortune cookies, right? It is the fortune cookie of astronomy. That's what it is, really. That is an example of pseudoscience. And it is difficult to spot now, right? It is everywhere. It's all over the internet. People are always, predicting things, and they're always telling you, it should be this way or it should be that based on pseudoscience and not real evidence. So Nostradamus was a famous prophet, and he would make these prophecies, and he would make sure that they were really vague, and they could only be proven after something had happened. So something would happen, he said, well, I predicted that, and then try to gain legitimacy that way, right? It's like those people that hold up the sign, the world's going to end on March 15th, for example. And one day someone's going to be right. One day someone's going to be right, and they're going to be like, listen, I told you, I knew it was going to be March 15th. But that is obviously pseudoscience. It's not based on anything. Research methodology is a systematic approach to gathering and analyzing information based on an established scientific procedure and techniques. And there's 3 common types of experimentation in field experiments: controlled experiments, single group, and pre-test and post-test experiments. These experiments include elements such as independent variables, dependent variables, confounding variables in all experimental material, the group or the class of the objectives or subject under study. So these are things that hopefully are not new to you, right? We know that based on all the years that we've spent in school, experiments often have independent and dependent variables, and that all of the language and the procedure and techniques have to align with this research methodology that is widely accepted across the world. And if you don't follow that methodology, the results you produce are not recognized by the international scientific community. They call it pseudoscience, and you're kind of back to square one. So this is why the methodology is very rigid. It is very predictable. They use the same techniques everywhere because they want to try to discover what is going on with certain situations, answer certain questions, and they can only do that if they follow the proper research methodology. Are field experiments real scientific experiments? So field experiments are kind of like Margaret Mead did, right? Like she went out and she observed things, and based on those observations, she established theories and explanations to questions. So the question here is, are field experiments real to scientific experiments? If you follow the proper procedures, sure. If you don't, then maybe not. Jane Goodall is a really an amazing example of this. I was actually lucky enough to meet her, but she spends a tremendous amount of time observing animals in the wild, right? She's dedicated years and years of her life observing how primates operate in their societies, how their cultures are organized, how there's the hierarchy, and how the dominant male and how they procreate, like all of these types of variables. And her scientific research is very well recognized all over the world because she followed well-established procedures in research methodologies. So you have to be careful when you engage in field experimentation, because if you don't follow the proper procedures, it's not necessarily going to be accepted. Mice or other lab animals are often used as experimental subjects. We know this. And we've discovered a lot using animals. And I don't think many countries and organizations would allow us to experiment on human beings. And so this is a difficult topic for people, because on one hand, we don't want to do a bunch of horrific things to animals. And on the other, we want to save lives. But is it worth it? Is it justifiable that we continue to experiment on animals in an effort to try to make our lives better, easier? I'll let you answer that one. Evaluating experimental designs. So well-designed experiments use the following criteria. They're unbiased. There's measurement, right? Those measurements are appropriate and they're reliable and they're accurate. Replicable, meaning the experiment can be reproduced by other scientists. And generalizable, meaning that the results can be generalized from a sample. Yeah, so, generalizables, they might do a study on a new drug, right? And they're not going to test everyone with the drug. They're going to test a small group, and then hopefully, based on the results of that small group, you can have some knowledge about how it will affect the entire population. Interpreting experimental results. Section in a scientific paper provides information on how the data were analyzed and which findings were statistically significant, right? So if you've ever gone through, and I'm sure you have, scientific papers, they could be 20 pages long, and it is the results section of the paper that provides the findings and what is statistically significant and what is not. And each time an experiment is replicated with a new sample and significant results are obtained, the confidence level becomes higher since the total sample size test becomes larger. Yeah, so this is what you need to understand sometimes. We discover things to be true, but then scientists will replicate that experiment to make sure that what we thought was true still remains true. And the more you can replicate something, the more evidence there is to provide the answer to the question you were asking, the stronger that answer becomes. The level of confidence we have in that answer is better. Ethical concerns in scientific experimentation. So this is something that continues to evolve. And although scientific experiments may be well designed and provide significant results, they may be inappropriate due to their violation of moral and ethical principles. Ethical considerations of informed consent, rights, and doing no harm are particularly important when dealing with human subjects. And this is something, if you look at experiments in the 1930s and the 1940s and 50s, it was not always taken into consideration. Like, look at the Milgram experiment we talked about in a previous class, where they were brought into a room and believed that they were going to be shocking somebody. That wouldn't fly today. That would not happen, because they would worry about the negative emotional trauma that they would inflict on the person who had to dial up the shock system where it said next to being lethal, right? That's something that we wouldn't put people through today, even if we were trying to discover the answer to something. During World War II, Nazi doctors performed unethical experiments on Jews, prisoners of war, and other prisoners. These activities have also occurred in the United States. I don't even know what the Tuscany study is, but I know that we've done things in Canada that were not ethical. Maybe that's the one where they gave people syphilis. I know that there was one where they gave slaves syphilis in the States, and that was to see how bad things would get without treatment. So it has been done all over the world, these types of unethical experiments. Should pregnant women or women who might become pregnant be allowed to participate in drug tests? Again, there's no right answer, right? Because maybe there's some type of sickness or disease or complication that happens only in pregnant women, and maybe there's a drug that could save them. But the only way to find out is to test on pregnant women. But do you take that risk? Again, this is why it's a chili pepper, because it's a hot topic and there's no right answer. Is it desirable, even possible, for science to become value neutral, meaning that the science doesn't have any values that bias their perspective? I don't know. I don't know if it can. Because can you ever become value neutral? Can human beings ever put all of their morals and values aside? Or is this something that we are always influenced by? It's another good question. Thomas Kahn and Scientific Paradigms. Okay, so in his work in 1962, he challenged the idea that science is a progressive and objective. He argued, and listen, it's hard not to see his point, that like other human enterprises, it's a social construct. It's a product of our society, and especially Western society. And it is biased because we have social expectations and professional norms, and we determine what is acceptable and what is not. And it is not true everywhere, and it has not always been true, and in one day it might not be true, right? Because our societies change, our cultures change. Things that were acceptable 100 years ago are no longer acceptable now. And I promise you, there's going to be things that are acceptable now in 100 years and will not be. And so this raises a really good question, is that can we really trust science? And maybe it's something like, listen, maybe it is the best tool we have right now. So until something better is developed, we're going to trust it with some skepticism, right? With some distance, with not diving in, head first and believe everything that you're told right away. Normal science and paradigms. So normal science refers to research based upon one or more past achievements, while paradigms is building on normal science provides an accepted view of the world, right? So a paradigm is a whole way the world is viewed based on a large body of research. And a scientific revolution or paradigm shift occurs when a new scientific theory is developed to replace a problematic paradigm. Einstein's theory of relativity is an example of a paradigm shift, as well as the example of the Earth revolving around the sun was a paradigm shift. The Earth not being round was a paradigm shift. All of these were big changes in the way that we think. Well, here's another great example: the continental drift theory. It wasn't until later, years later, that continental drift, which was proposed in 1912, became accepted by the scientific community. Right, that the continents at one point were all put together. You know, in 1912, Mr. Alfred there sat down and said, "You know what? It looks like these were once one piece of land." And people said, "No way." And it took years and years for that to be accepted. That was a huge paradigm shift in the way people think. So science and the scientific thinking has generated enormous benefits through humanity. Yeah, it's we are here today and we live as long as we live, largely based on scientific discoveries that came before us. Having said that, as critical thinkers, we must be aware of its limitations and the temptations of all pseudoscience and the possibilities that other explanations may exist, that maybe things are beyond science. We must use evaluative criteria when considering scientific reasoning and recognize that new ideas may hold answers to questions that existing paradigms cannot resolve. Okay, that is a quick overview of Chapter 12, Science. There's a lot in there, but most of it's pretty straightforward. You've seen most of this before. It is not brand new information to you. If you have any questions about any of this information, as always, don't hesitate to reach out and ask, and have yourself a great rest of the day.